So now, let's take a look. We have a square wave coming out of our function generator. So let's take a look at the function generator. Well, we have our square wave because the square wave button's depressed right there. The square wave button's depressed right there. And we want 15 hertz. So let's just confirm that we have 15 hertz. In other words, the 10 button's depressed. And then the knob is turned to, let's see, 1.5. So good. 1.5 times 10 is our 15 hertz. So I want to just take a look at the RC circuit right away. We'll set the voltage in a second. But notice that the function generator is going directly into channel 1, and that these are coming directly out, so we can put in the current with this. So into the R. The R is already in series with the first capacitor, and then out here. And then channel 2. Channel 2, we want to measure the potential drop across the capacitor. So here, and then here. All right. I'm about to put on both channels, but take a close look. Take a close look at that graph. All right. Now back here, I'm about to put on both channels, and we're going to see. Let's get the square wave, and let's see both channels now. Bam! Look at that. The discharging, charging, discharging. Just like I told you. Come here. You didn't believe me, did you? You thought I was just wasting your time. How many labs have we been together now? I've never lied to you. Never. Okay. So now, let's go back to channel 1, and let's set our voltage. So we need this knob here on the function generator. The amplitude will control the voltage. So I turn it up. And I want 8 volts. I turn it up to 8 volts. So that means that if I have the units of 1 volt per box, and there's 8 boxes, I just need to have the top of the square wave to be at the top, and then the bottom to be at the bottom. 8 boxes, 1 volt per box, 8 volts. All right? And also, notice channel 2 is also the same, 1 volt per box. And now I just want to look at the decay. All right? So now, to zoom in on one of the decay curves, we switch the time to 1 millisecond. 1 millisecond. And there we go. And now, what we need to do is we need to put, we need to have, where's that tip? There it is. We want to put this tip here in the upper left-hand corner. So I use these knobs. There we go. Okay, great. So now look, we have each box on the vertical represents 1 volt, each box on the horizontal represents 1 millisecond. So now I can find, let's see here. So at 8 volts, time is 0. Good. So let's see, at 7 volts, each of these little divisions represents 0.2 milliseconds. So I got 0.2, 0.4. Doesn't look like it's quite halfway. It does not halfway to the 0.6. So 4.3, I think. So I see. So it's 0.43 boxes, 0.43 milliseconds for 7 volts. All right, and then we do the same thing. We do the same thing for the 6 volts, the 5 volts, and then I want to jump to the 4 volts, the half-life. So let's see. So 1 box, 2 boxes, 2.446, I see. About 2.46 milliseconds for the half-life. And then you go on until you get to 1 volt. And then that's the data to find your graph. Do your linear regression, find your slope, With the R, you can calculate C. All right, next, we want to do the same thing, except we want a parallel setup. So, here, and then here, and then here. These two capacitors are now in parallel. They share the same potential drop across them. All right, so let's think about this. If each one of these is around 0.1 microfarads and they're in parallel, that means we should double our effective capacitance to 0.2. Let's just directly confirm that. So let's see. Here and here. What'd I tell you? Around 0.2 microfarads. All right. So let's see. If we doubled the capacitance, we should have doubled the half-life. Let's see. Let's go back. Okay. Yes, I can't wait. I need to see. So current goes in through the R. Okay, I gotta be careful here. I can't put the low end here, or it's gonna completely ignore the capacitors. It's gonna take the passive least resistance right back. So I gotta put it other side, and then channel two across the parallel capacitors. So here and here, and look. What did I tell you? Okay, so look, the half-life has doubled. All right, so I can actually switch back and forth. Here's the single, here's the double, and we can see, look what's happening to the half-life. The single capacitor, the parallel, and the half-life doubles. All right, now we want to do the same thing with the series. So we'll start over. All right, so now series. This capacitor in series with the second capacitor. All right, so let's see, if both of these are 0.1 and they're in series, the effective capacitance should be 1/2 of that, 0.05. So let's see here. So measure into here and then out here, 0.05 microfarads. 0.05 microfarads. So now that means that the half-life should be half of the single one. Let's see. Okay, so we gotta be. Let's see here. All right. So now into the R, through the first capacitor, through the second capacitor, and out here. Then channel 2, we want to cross both capacitors. So let's see. So the first capacitor starts right there. Out here, and then out there. And then out here. And look. The half-life is now half of what we had with the single one. So measure that, and that's how you find your data. And we have one more issue before we conclude. One more issue. We have two potential systematic errors. We have a 600 ohm impedance of the function generator. Is it an issue? Is it not an issue? You'll tell us. You'll take that 600 ohms and you'll divide it by R1 plus the 600 ohms, times it by 100 to make it a percent, and compare it to 5%. If it's greater than 5%, we can't ignore that. But if it's less than 5%, we'll call it negligible. The second systematic error has to do with the mega ohm impedance of the oscilloscope. And that might affect your last 2 points on your linear regression. So try removing those last 2 low voltage points. Remove 1, remove 2, see what happens. Things improve. Determine how to handle those points from there. And that's it. You are now masters of capacitors.